Okay, so now I probably have to reduce. Thank you very much. So my presentation, I think, starts very much with questions that you can already find in this classic book. It's very much, of course, questions of harmonic analysis. When you have a system with certain symmetry, you want to expand all the functions that you're looking at in terms of an adequate basis of functions. Like you do this in Fourier theory, you have translational symmetry, and you expand everything in terms of plane waves. And of course, in conformal field theory, you have all sorts of correlation functions of observables, and you want to expand them in an appropriate basis of functions, and these are the conformal partial waves. Okay. So now here is an expert audience on conformal field theory. So sorry, so you know when you do this, let's say for the beginning we look at just correlation functions of local operators in the conformal field theory, as was done sort of in the early days of conformal field theory. Then you know 2- and 3-point functions are fixed by conformal symmetry. 3-point functions are fixed up to some number, the OPE coefficient. And sort of the first interesting quantity that has a non-trivial expansion in terms of these conformal partial waves are the 4-point functions of local fields. And so 3-point function I said here is a constant, which is dynamical determined, and then this vertex function, a 3J symbol, which of course is known. Many of you could write it down, I think, or maybe all of you could write it down immediately if these are 3 scalar fields. If one of them is in a symmetric traceless tensor representation, some of you can also write it down, but you can definitely find it in the book. Okay, so this is a known object, a known relatively simple function. And then this conformal partial wave that appears here that you use to expand 4-point function is some function that depends on 2 variables. These are the 2 conformal cross ratios you can build from 4 coordinates in a d-dimensional space. You can essentially write like this, and that actually has a particular meaning. It's an integral representation that also appears, of course, in this book. So this conformal partial wave can be written through this integral. Okay, that looks, it takes a moment to digest. I don't want to really go through this, but of course many of you have seen it, and I think Gerhard also showed this in his talk on Wednesday, if I remember correctly. Now when you see this integral representation, I mean, it's of course one way to build this function, but of course it hides many properties of this function. It's not immediately clear like what are the properties of the function, how does it depend. So it depends of course on the cross ratios and also on the so these A and B parameters would be differences of conformal weights of the 4 fields. So here I assume that we have 4 scalar fields, external scalar fields. Delta and L would be the conformal weight and the spin of the exchange field. So you may wonder, how does it depend on A and B and on delta and L and on Z and Z bar? So in particular, does it have poles in these parameters? What are the residues of these poles? I mean, all this is not very explicit when you write down, or not clear when you write down this integral representation. So this is like the first and sort of classical example of a conformal partial wave. And of course, now there's many more, in fact, where you can ask similar questions. In fact, Jean Bernard highlighted in his review of 2-dimensional CFT that in the context of 2-dimensional CFT, at some point it was understood that not only local operators are important, but also higher dimensional objects like defects, interfaces. And in higher dimensions, when you go to higher dimensional conformal field theory, that of course is even more important because there are many more higher dimensional objects. And like one example, of course, is that many conformal field theories in 4 dimensions, let's say, are gauge theories. And in gauge theories, of course, you have Wilson loop observables, right? So not just local operators, but also Wilson loop observables. And you can also ask the question, what happens if you compute, for instance, a 2-point function of 2 Wilson loop observables in a gauge conformal gauge theory? And again, it turns out that there's a particular set of conformal partial waves in which you can expand such correlation functions. Okay, Now in this case, in fact, if you go to a four-dimensional gauge theory, conformal gauge theory, let's say n equals 4 super Young-Mills, just as a concrete example, and compute the two-point function of two Wilson loop observables, it turns out that in this case you have three cross ratios, conformal cross ratios. So you get some kind of expansion in terms of special functions of three variables, okay? And again, you can ask the question, what are these functions, okay? So you can write down similar integral representation like the one I showed you for the conformal partial waves for scalar operators. But again, it doesn't really give away sort of the real nature of the functions. And so the question is, I mean, how do they really depend on the cross ratios and all the parameters of the problem, like the conformal weights of the fields and so on and so forth. Now, in fact, if you sort of went to the zoo of special functions, these are some special functions, these conformal partial waves, right? If you went to the zoo of special functions next weekend, question is, where would you actually go? So would you go sort of to see the dinosaurs, like the hypergeometric, Gauss hypergeometric function, I mean, whose mathematics was developed back in, well, I mean, centuries back, but of course most profoundly, I guess, in the all through the 19th century? Or would you go somewhere else to some kind of modern creatures, like modern, recently discovered species? And in fact, yeah, one of the key messages I will show you later, sort of the cages that you have to turn to. And in fact, turns out that these special functions are extremely modern special functions who were completely unknown to the people in the 19th century, and in fact are just researched on right now by a large group of mathematicians, in fact also physicists, but in a very different field. So before I do that, let me continue a tiny little bit to look at some questions that you can already find in this classical book, and that I think what I'm going to tell you has some bearing upon. So coming back, so again, I mean, again, conformal partial wave expansions are important to everybody working on conformal field theory, not just people that want to do bootstrap. I mean, even people that work with Lagrangians and expansions and stuff like that. But if you do bootstrap, of course, then as has also been reviewed, you want to get this nice self-consistency condition from associativity or crossing symmetry. And one way of writing that is that, of course, you can decompose the four-point function in these two different ways with the OPE coefficient here and then these special functions that I've talked about in the previous slide. Now, these special functions, of course, depend on the conformal weights and spins and, of course, on the cross ratios on both sides. Now, we know, of course, a nicer way. So whereas, of course, these coefficients that you try to solve for do not depend on cross ratios. They just depend on the weight. So there's a nicer way of writing this crossing symmetry equation, and namely by basically bringing this to the other side and writing the crossing symmetry equation in terms of, I mean, without any cross ratios, just in terms of functions that depend on weights and spins. And so this is particular scalar product here of T and S channel blocks appearing here. In the mathematics literature, this would be known as the 6J symbol, or in physics, as the crossing kernel. So you can ask similar questions here. This crossing kernel will actually depend now on 6 conformal weights and maybe spins. So what kind of function is this? Okay, do we know this function? And how does it depend on all these parameters?
Is the second equation a convergent equation?
Okay, so I mean, I didn't even write it in. I mean, there's many versions of this equation. So yeah, let's. So I wrote it here with the sum. I mean, when I think of this equation, normally I think of it as an integral equation where I integrate over imaginary axis like C, and so then we might readdress this question. So I think I don't want to really go through this right now. So what I wanted to highlight here is that that there is a bunch of numbers, some kind of. In fact, you should think of that as some kind of integral kernel. And you want to construct this quantity to write down these equations in a meaningful way. So now the main result I want to show you today is that that now these questions that I posed on the previous slide and that were very much also posed in this book, they possess an answer, and the answer comes sort of in two steps. So first of all, what I want to try to convince you of is that these conformal partial waves, all the conformal partial waves I talked about for 4-point function or these defects or Wilson loops, they are actually wave functions of a quantum mechanics problem, okay? So that you can write down a beautiful Schrödinger equations, and the wave functions that solve these Schrödinger problems are actually these conformal partial waves. And this statement is extremely universal. Now, in fact, I told you before that, these conformal partial waves are functions both of the cross ratios and of the conformal weights and spins. And in fact, there is, in some sense, integrable Schrödinger problems determining both the dependence on the cross ratios and on the conformal weights. In fact, what I'm going to show you is that the dependence on the cross ratios, this is a kind of quantum mechanics problem known as the Calogero-Sutherland Hamiltonian. Now, if you have never seen this before, don't worry, I will show you. That's a particular quantum mechanics problem with a particular potential. And the dependence on weights and momentum, or angular momenta, is also determined by some integrable problem, which is sometimes called relativistic Calogero-Sutherland or rational Roisener-Schneider model. And so this is, in some sense, the main message of my talk. Now, in fact, I told you very early on, I was an undergraduate student, I visited Sofia, and I remember I gave my first talk in Sofia, and I think Ivan was a little nervous about this, having such a young person give a talk in a seminar. So he called me into his office a day before, or 2 days before, and gave me some advice. And I remember one of his the advice that most stuck to me is, like, I should think of one message I want to convey. One message. One message is enough for a talk, okay? And to this very day, I give this advice to my young students. I think it's a very good advice to think of that one key message. And so the one key message of this talk is that the conformal partial waves that you need to expand all sorts of correlation functions in the conformal field theory are wave functions of integrable quantum mechanics problems, okay? But then I'm going to violate Ivan's advice today, because I'm a little bit afraid some people might say, so what? Now you've just shown us that this is wave functions of some quantum mechanics problems, but what do I really learn from it? And so I will have sort of a second message, is that these conformal partial waves, or these wave functions of these integrable Schrödinger problems, they are actually, again, identified with Euclidean Heckman-Opdam hypergeometric functions. And that's one of these species of modern hypergeometric functions that mathematicians know a lot about. So the main message of the second part, so if you want this talk as two equations, conformal partial waves are wave functions of some nice quantum mechanics problems. And these nice wave functions, they are Heckman-Opdam hypergeometric functions. And what this should signal for you is there's some names of mathematicians attached to this. So this is actually very well studied hypergeometric functions. But Heckman-Opdam did this work starting in the 80s, and then many, many, many other people joined into this. I mean, a person like Cheretnik, Matsuo, of course, Kornbinder, so Stockmann, Ettinghoff. So there's lots of mathematicians, and also recently, somehow in the context of supersymmetric gauge theory, there's work in somehow related issues. So good. So my plan is, in the first part, I will show you how these quantum mechanics problems actually appear in this problem of constructing conformal partial waves. And so at the end of this part, I will have done like my perfect talk with one clear message. And then we will see in the second part, I will try to convince you and show you some of the beauty of the mathematics that was developed starting from 87, I believe. Now, what is I find quite amusing is that, of course, conformal field theory, as we heard on Wednesday, I mean, the early developments were roughly 50 years ago, like around 1970 was the formulation of the bootstrap program. In fact, at the same time, or just slightly after this, these quantum mechanics problems, like the hyperbolic Lodger-Sutherland and Royce-Schneider models were first formulated, but of course there was no apparent connection between the two subjects. And then came all this revolution in two-dimensional conformal field theory, and right slightly after this, I mean, was all this revolution in the theory of hypergeometric function that was initiated through studying these quantum mechanics problems. And it was only quite recently that it was actually observed that these two fields actually have a relation, and that basically this study of the Schrödinger problems actually solves the problem of constructing conformal partial waves in very general terms. All right, so that's the introduction. So let's now start with the first part. So I decided, because this is a talk on the conference harmonic analysis, I will give you sort of a very mathematical approach now, a harmonic analysis approach to what conformal block or conformal partial waves are. So we're going to realize them as functions on the group, on the conformal group, okay? So we don't think of them as sort of functions of x's, 4 coordinates or cross ratios, but as functions on the conformal group. Very much like when you, for instance, construct representations of this rotation group or spin group, you can realize them as spherical harmonics, which is like functions on the quotient of the group SU2. So conformal partial waves in this, so I will just do this exercise, only for the simplistic case where we have 4-point function of local operators, okay? And then I'll say a little bit about generalizations. Now the first thing is, of course, we have to prepare the principal series representation that Gerhard talked about on Wednesday. And we want to realize that as functions on the conformal group. Okay, so this is well known. In fact, again, now you look up the book in the book, so you see how to construct that. So you take functions on the conformal group. G is the conformal group, taking values in some finite dimensional vector space. Now, actually, here I must admit I deviate from notations in the book, unfortunately. So for me, this K is not the maximal compact subgroup of the conformal group, but it's the product of the group of dilations and rotations, okay? So I apologize for that. So you pick a representation of dilation and rotation. That is, you fix a spin and a conformal weight. And so, and then you look at, and so this is this choice of this finite dimensional vector space here. Then you take a function from the group into this finite dimensional space, and you require that this function has the following covariance property. When you shift it by rotations and dilations from the right, it should just kind of covariantly rotate. Okay, so this pi here is a representation of dilations and rotations on the fiber, on the image of this function f. And n is the exponentials of special conformal transformations. So it should be invariant under right shifts with special conformal transformations. Okay. Now, you can think of this, well, either as covariant functions on the conformal group, or you think of it as functions on the quotient of the conformal group by special conformal transformations, dilations, rotation group. And if you divide the conformal group by special conformal transformations, dilations, and rotation group, you're left with translations. So roughly, these are functions of d variables, okay, taking values in some finite dimensional space, okay? So that's a well-known way to realize. So this space here, of course, carries an action of the conformal group. We have only used covariance properties with respect to the right action. We can now have the full left action of the conformal group on these functions. And so it's a representation of the conformal group. It turns out under certain conditions on delta, it's a unitary principal series representation of the conformal group that you can realize in this way, okay? Now again, that's all was all known, of course, in this all appears in this book. Now in the book, there's another statement. So now we have this principal series representation, and we are asked to construct invariance in the fourfold tensor product. That's our mathematical definition of what a conformal partial wave is. It's a conformal invariant in the fourfold tensor product of principal series representation. So we have to start building tensor products, and it's actually quite useful that the book also contains a result of what the tensor product is of two principal series representation, how we can realize that as functions on the group again. So the claim is that we can do this. Again, we take functions on the group. Now we take image in the tensor product of these two. So for each of these weights and spins, we have one finite dimensional representation of the group K. So we take the tensor product of these finite dimensional spaces. So we take functions from the conformal group in this finite dimensional space. And now we want them to be just covariant with respect to right translation with dilations and conformal transformations. And so we require just this property, no invariance with respect to n. And of course, these functions, roughly, you can think, again, I mean, you just have covariance with respect to dilations and rotations. So what you don't specify is the behavior with respect to special conformal transformations and translations. So these will be functions of 2D variables, okay? And they take values in this finite dimensional vector space, okay? And it's a theorem in this book that is proved in this book that this is, I mean, this space, of course, carries again a representation of the conformal group. It's now a highly reducible representation of the conformal group. And it's the same representation that you obtain by taking the tensor product of two principal series representations, okay? Good, so now we're getting there. We have to not take the twofold tensor product, but we have to construct the fourfold tensor product of the principal series representation. So let's do that. So we want to construct, yeah.
Dark theorem, or is this obvious somehow? Is there an intuitive explanation of why this is?
I mean, there's probably all sorts of intuitive explanations. Yeah, I mean, that's it looks roughly right. I mean, so I think there's intuitive. I mean, as you just pointed out, some of the special conformal transformations are just like translations of a second point at infinity, and so somehow you see that you get this. But then you can again read the full proof in the book. So now we are instructed to compute conformal invariance in the fourfold tensor product of these principal series representation, and in fact it turns out that we can do this. In fact, here I should maybe show you the steps that lead to this. So we took the fourfold tensor product and realized, well, so fourfold tensor product, we think of twofold tensor products, and the twofold tensor products we realized on G mod K. And now I'm going to write, I mean, it doesn't really matter whether I take left or right quotients, of course. So I take twofold tensor product of two of these representations, realize it on G mod K, and the other two on G mod K. And now I'm supposed to take invariance with respect to G. So I have an action of G by left translations from here, right translations from there. When I divide by this, of course, I use the fact that G times G mod G is G. And so when I divide by this G action, I get a double quotient like that, okay? So that tells me that now I can realize these conformal partial waves, the invariance in the fourfold tensor product, as kind of functions on the group which have left and right covariance properties with respect to K, okay? So they take now values in the general case for spinning external fields in the tensor product of four of these finite dimensional representations with these covariance properties. And if you go through the analysis, you will see that this double quotient actually is two-dimensional. Okay, so this is not entirely obvious at first because, I mean, when you divide G mod K, you get something like 2D dimensional. Then it turns out the second K action is not free, so there's a huge stabilizer that kicks in once you go beyond 3 dimensions. So you have to take care of that, but the quotient is actually a two-dimensional space, and that's the space of cross ratios, okay? And so you can think of these functions either as I said, double covariant functions on the conformal group or functions on this two-dimensional double coset space, okay? Good, so now we have found a model for these conformal partial waves. Now let's try to understand what they are. So now we do sort of our harmonic analysis. So the idea now would be that we start with a Laplacian on the conformal group. That's a beautiful second order differential operator. Or we can also do higher order Laplacians, Casimirs, of course. Let's fix to the second order, a Laplacian second order Casimir. It's a differential operator on the conformal group that, of course, you can write down in any set of coordinates that you want. It turns out that there's a nice set of coordinates that respects basically this double coset structure in a nice way. That's kind of introducing some sort of Euler angles on the conformal group in a specific way. And you see the Laplacian, of course, is left, right invariant, so it descends to this double quotient. And it's a simple exercise to just compute what the second order differential operator looks like on this double quotient, right? So double quotient is two-dimensional, so you get a second order differential operator that will just involve like two coordinates, okay, two of these Euler angles that you introduced on this conformal group that you use to parameterize this quotient. And so this is a very simple exercise. You just sit down and do your computation, okay? You choose nice parameters, you write down the Laplacian, you restrict to the space of functions that have these left and right covariance properties, and you get, of course, a second order differential operator. And it turns out, once the dust settles, and you have to conjugate this by some simple scalar function, which also has a geometric understanding, this second order operator takes the form of a Schrödinger of Hamiltonian. Okay. So in this particular case, for the four-point function of spinning external operators, it can always be written in this form with some kind of standard kinetic term plus a potential. Okay. Yes.
Sorry, so at which point do you start to distinguish between the channel ST or U channel?
So for me right now, this does not matter. I'm just looking at the basis of functions. It's the same basis of functions, right? I'm trying to construct a basis of function that I can use to expand my correlation functions in. Okay, so.
Because so far there's no relation to OP. You just find some functions, but then you have to explain how they relate to OPs.
How they are related to OPs. Yeah, so so again, the problem here is a purely kinematic problem, right?
No, not, because if you want to use this block for the conformal bootstrap, you have to say that
first of all,
will appear on the view of some operator, not just the basis. So at some point you have to provide this information.
Maybe you have to specify what information I'm supposed. So I'm providing a construction of a basis of function in which I can expand, let's say, four-point function of any spinning field.
But you want to say that the coefficients of this expansion are going to be B coefficients, not just some arbitrary numbers. If you want to relate to physics.
Yeah.
But answer it to me.
Okay.
What did you say about the function M of U? It has some geometrical meaning?
So it's basically the volume of an orbit. So you have this k times k action on G, and the volume of the orbit through a particular point is basically this function M. So it's easy to compute. Yeah, sorry, D2 was the Laplacian, right, and so restricted to this space of double covariant functions, and then so maybe, I'm still trying to think of what kind of answer I should give to this. So in fact, the first time we hit upon this relation with between conformal partial waves and Calogero-Sutherland was actually not through this harmonic analysis argument, but was looking at the differential equations for conformal partial waves that were derived in Dolan-Osborne, a paper that was mentioned also here on Wednesday, and you can then explicitly show that the second order differential equation, the eigenvalue equation for this problem, is actually equivalent to these equations that Dolan-Osborne used in their papers to characterize scalar conformal blocks. But of course here this is already significantly more general, because again, this explicitly includes also the case of spinning conformal blocks. So typically for spinning conformal blocks, this potential here will be some kind of matrix valued potential. If you have just scalar external field, then it will be a scalar potential. And the scalar potential you can work out takes the following form. So it is maybe at first, when you're not used to these things, maybe looks a little frightening. So it's a function of two variables, ui. Again, these are some kind of Euler angles on the conformal group. In fact, they're also directly related to these radial coordinates that Volker first and Ryschkov introduced. So they appear very natural here as special coordinates on the conformal group. And there's a bunch of parameters here. So A and B and then D. So D is really the dimension of your conformal field theory. So if you do a 4-dimensional conformal field theory, D is 4. If you do it in 6-dimensional conformal field theory, D is 6, and so on and so forth. A and B are related to the conformal weights of the external fields. And so this is the potential that you get. And so what you see is you get some kind of external potential here, parameterized by two parameters A and B, and then an interaction term depending on the differences and sums of the u's with a coupling that is given by the dimension D. Now when you go to D equal 2, you can see all these terms here vanish. So then you just have two decoupled potentials. So that's basically, you recover that there's this independent left and right movers, and in fact it also works for D equal 4, maybe slightly less obvious, but it explains some of the formulas. All right, so that's the result. Okay, so indeed it's a rather simple exercise that you do. You start with this harmonic analysis definition of what a conformal partial wave is. You work through these steps, and you derive this second order operator whose eigenfunctions are then the conformal partial waves. Eigenfunctions of the Laplacian on the conformal group. Now, yes? Yes. Yes, exactly.
But that would be in the 1, 2 going to 3, 4. So that's this equation. But you seem to say that there's no information about which channel you're expanding.
Yeah, at this point we have not. I mean, so now.
If I start switching around the external operator.
I mean, it's the same set of basis functions, right? If you switch them around, I mean, you.
Depend on the external operators.
Sorry.
Don't they depend on the dimension?
Oh yeah, sorry. So if you want to do it for the T channel, so that's your question. Then you would take, in terms of A parameter, delta 1 minus delta 3, and delta 2 minus delta 4 is the B parameter. So you would have some A prime and B prime, and so these parameters would change for the T channel. Yeah. So okay. So good. Yeah. So of course, if you think of having delta 1, delta 2, delta 3, delta 4, then somehow this equation is now for the S channel, let's say, with these parameters. If I want to do the basis set of functions for the T channel, I would just have to construct an A prime, which is delta 3 minus delta 1, and so on. But I mean, it's the same type of problem. It's just different coupling constants. Yeah, okay, so it was actually probably clarifying this issue to other people as well, so thanks a lot. Okay. Now, what I so this is one such example. Now, the story that I told you is actually extremely general. So you can do this exercise for other cases. And as I said, you can work out, and we did work out sort of these Calogero-Sullivan Hamiltonians for some spinning blocks, I mean, with spinning external fields, particularly for defect blocks. So for instance, the blocks that you need in order to expand the two-point function of Wilson lines in the 4-dimensional conformal field theory. I told you before they depend on 3 cross ratios. And you can go through the same type of exercise and find that, again, these functions of these 3 cross ratios are also wave functions of similar Hamiltonian, but for 3 variables, U1, U2, U3, and a very similar interaction. You can, in fact, do this also for a superconformal group, not just for the conformal group. You can have apply the same kind of strategy to study conformal partial waves for super conformal blocks, thermal blocks, multi-point correlation with more than 4 external field. So somehow you always end up with the same type of Hamiltonians. Okay, so it's a completely universal relation somehow. Now, of course, I could go and show you examples what these things look like, but I think it's more important to show you a little bit why this is relevant information. Yeah. I will not talk about thermal blocks. No, as I said, this slide is talking about all the things I'm not going to talk about.
Can you then comment on how, so thermal blocks correspond to theory we should use on, like...
Can we, because I'm already a tiny bit late, can we defer that to discussion or... again, this was... So this was sort of the harmonic analysis part of the talk, but my title also contains integrability. And so integrability, so again, the main message of this talk in some sense I've now provided. I've showed you and hopefully convinced you that conformal partial waves, like the ones that appeared like in the 70s or like other conformal partial waves that one needs for other correlation functions, in particular of non-local operators, they're all wave functions of Calogero-Sutherland problems, okay? So that's somehow the key takeaway message. But in the final remaining like 20 minutes, we started 5 minutes late because of the technical problems. I want to show you that this is not just rewriting like some kind of Casimir equation, but this statement comes along with a very profound insight on these wave functions. And that is tied to the integrability of these quantum mechanics problems. Now, let me, I haven't really, I didn't name them in the beginning. So this type of Hamiltonian that I showed you 2 slides ago belongs to a class of Hamiltonians that is known as Calogero-Sutherland Hamiltonians. So the characteristic would be these potentials which have, in this case, hyperbolic singularities here, or 1 over square of hyperbolic function with some coefficients, okay? And so the first example of this type, in fact, in some sense was the Poeschl-Teller problem that was studied in 1933 by Poeschl and Teller. That's an example with a single variable Hamiltonian. And it's essentially, of course, just the potential, in this case, Poeschl-Teller potential is just this thing here for 1 variable u, okay? So you can ask the question, I mean, what can you do when you have, so the potential would then look like something like this. So depending on parameters a and b, you have something like this. You have an exponential wall somehow at u equals 0, and then you have some kind of thing that goes to 0 at infinity. And so you can study the quantum mechanics of this potential, okay? And Poeschl-Teller, of course, did this in 1933. They noticed that the Schrödinger equation for this problem, they can map to the hypergeometric differential equation and, of course, constructed solutions in terms of hypergeometric functions very explicitly. And then I think in the 70s, people started to wonder about exactly solvable multi-particle generalizations of this. And so they tried to put like several particles now with coordinates u1, u2, u3 into an external potential and couple them through some interaction terms. And they were wondering what interaction terms you can actually put to keep this problem somehow exactly solvable or integrable. Okay? And they came up with the idea that, I mean, sort of such integrable interactions that you can introduce, like, again, let me make this explicit here. So I pointed this out before. So this is basically 2 external potentials for 2 particles here, and this is an interaction term. And you can wonder what interaction term you can put. I mean, of course, if d equals 0, d equal 2, you have no interaction term. That's, of course, 2 copies of a solvable problem. It's solvable. But the question is, can you introduce interaction and keep the problem solvable? And the answer is basically yes. I mean, you can roughly classify such solvable extensions or interactions by choices of root lattices. Okay, so this is a mathematically very advanced audience. So I think you can almost see sort of a root lattice in these terms here. You see that it has two interaction terms in the external potential that corresponds, well, to two different roots somehow in direction 1, two different roots in direction 2, and then there is these two terms here which correspond to the positive roots of a BC2 root system. Okay, so this potential is attached to a BC2 root system, and you can generalize that to a higher number of particles. And so, so now, so this is sort of an interesting extension of this old classical Poeschl-Teller problem and the sort of theory of hypergeometric functions. And in fact, studying these quantum mechanics problems was really the origin of much of the modern theory of hypergeometric functions that I alluded to at the beginning. Now, so I'm not sure I really have the time to go through this so slowly, but I'll try. So again, what I said on the previous slide is, of course, the simplest case when you have just one variable is just this Poeschl-Teller Hamiltonian, and of course everybody knows that the wave functions take the form of a hypergeometric function. Okay, so this hypergeometric function, of course, is not just the wave function here, but it's also the conformal partial wave for one-dimensional conformal field theory, right, according to what we saw before. And again, so the argument here is basically the cross ratios, and these parameters depend on the weights and spins of the external field. And so even this problem, in some sense, is integrable. Of course, in a one-dimensional problem, that's maybe not so remarkable. But in fact, there's an observation that you can also check, like on a little sheet of paper, that this Poeschl-Teller Hamiltonian, the one variable case, you can write as a square of a first-order operator. Okay, in fact, almost. So the first-order operator cannot take. So first order has this first-order piece and then some kind of function, but this cannot quite be a function. In fact, it has to be a function taking values in the reflection group. This problem has reflection symmetry here. I didn't write this part. And so there's a reflection associated to this. And if you can actually solve this this equation here, if you allow sort of for potentials or for functions here that take values in the reflections. Okay, so if you do that, then you can actually take the square root of the Hamiltonian. And so the statement is, if you square this guy and restrict to symmetric functions, then you will get the Hamiltonian. Okay. So in that sense, there's a direct relation to a first-order operator. That's also known as Dunkel operators. And so once you have this first-order operator, you can actually write down, so it's a nice first-order operator. So attached to this first-order operator is a Knittich-Samlochikov equation, like the ones that we know from two-dimensional conformal field theory. But remember, now we are doing a conformal partial waves for the global conformal group in d dimensions. And you can write down this, straight from this expression. I'm not going to go through this here, this kind of Knittich-Samlochikov type equation. And you can, of course, solve it, like you learned, I think Jean-Bernard talked about this Coulomb gas representation. You can write down some kind of Euler-type integral for the solutions. Now, so this was all about one variable case. Of course, nothing new here. But the remark, so I should maybe also mention that that there are some more equations you can derive from here. So I guess maybe I leave that up to questions. So this all generalizes now to the multi-variable case, like again for a scalar or for 4-point blocks in a d-dimensional theory, we have a two-variable problem. So it turns out that again, this Calogero-Sutherland Hamiltonian, the one that describes the Casimir equation for conformal blocks, actually can be written as a sum of squares of commuting first-order operators. And these first-order operators in a slightly condensed notation look like this. So like you saw in the previous example, they take values here, these functions take values in the reflection group or sort of in the Weyl group of the BC2 root system. That's in this case a group of order 8. And so so these are two first order operators. You can check explicitly that they're commuting with each other, and that when you take the sum of squares of this operator and restrict to the symmetric functions, that you actually recover the Cauchy-Sutherland Hamiltonian, the one that I showed you to describe the. So similarly, of course, from here you can directly write down a system of Cauchy-Sutherland equation. It turns out that this is a now 8x8 matrix equation. And I guess you can then try to write down similar Coulomb-Gas formulas for the correlation function. But this is something we haven't really worked out in detail. I think I skipped this extra structure. So in fact, from these first order operators, you get more properties of these functions, not just these Cauchy-Sutherland equations, but you also find some kind of differential shift equation. Similar to the hypergeometric function, you know, when you have the hypergeometric function, you can differentiate it, and it shifts all the parameters by 1 unit. So this you can also derive, of course, from these Dunkel operators in a very systematic way. It turns out for this 2-variable case, there's 2 differential shift operators, which you can work out by a straightforward procedure that kind of shifts parameters. And this allows, in this case, to shift the parameter A, sort of the difference of conformal weights, and also the parameter D, the dimension of space-time, in that case by 2 units. So you can use these operators to derive relations systematically between conformal partial waves that in dimension that differ by 2. Now, of course, I should say that, I mean, these relations for this case of 4-point function, of course, you can also find in the later work of Dolan and Osborne. But the derivation that goes through these Dunkel operators is a lot more general, and it immediately also applies for these multivariable case, like for the conformal partial waves that you would need to decompose Wilson lines in the 4-dimensional gauge theory. So that's part of the integrable structure. So I have to speed up even more because this is only half of the integrable structure of the problem. There's a whole second world of integrable structure in this problem. And the way I want to talk about this is, you see, when you have a free particle, of course, it satisfies this Schrödinger equation. Okay. Now the wave function, of course, then looks like that. It's a plane wave. And you observe that, of course, it has the same dependence on P as it has on U. So it satisfies also a second-order differential equation with respect to differentiation with respect to P. Okay, which looks the same way. So somehow that's a dual Schrödinger equation that describes the dependence on P. Now in this case, of course, you see that this equation here is polynomial in derivatives with respect to U and polynomial in P in the momenta. And so the dual equation has the same property. It's polynomial in P and polynomial in U. But our equation that we started with, so you can ask, is there a similar fact for our wave functions of this Cauchy-Sutherland model? So when you look back at this equation, maybe I like the most explicit one, or maybe even Poeschl-Teller would be enough. So you see you have a polynomial in U, but the potential now depends in the derivative of U, but the potential depends on exponentials of U. So you expect somehow when you dualize this problem that you will have something that is an exponential of derivatives in the momenta and a rational function of the exponentials of U. So I'm not sure that. So when you work this out, in fact, you find that indeed there is some kind of quantum mechanics problem that describes the dependence of these conformal partial waves on the momenta. That means on the conformal weights and the continued spins. And that takes the form of a difference equation. That's a statement that it does not involve polynomials in derivatives, but exponentials of derivatives. Exponential of derivatives, of course, are difference operators, shift operators. So it takes the form of a difference equation. So these conformal partial waves that we discussed up to now they satisfy difference equations of this type. So you see here, now you have a second order difference operator acting on the wave function, on the shifting the momenta, the dual variables, and the eigenvalue is now determined by the cross ratios. So it's completely dual to the previous problem. And so this problem is actually a known, also very well-known difference equation that is called the Hamiltonian or Schrödinger equation for the, in this case, rational Roysner-Schneider problem. And it has the same nice features as the Calogero-Southern problem. It's integrable. You have first-order operators that commute. You can build some kind of difference version of Knittner-Samolotchikov equations, and so on and so forth. Shift operators, different shift operators. In this way, you can recover many of these shift properties. So Dolan and Osborne in their paper wrote down many shift operators, shift equations for these two-variable case. And in fact, you can check that they all kind of arise from this feature. For instance, there's one complicated equation that they write, which can be recast after a little bit of modeling into this very simple form. And so all the equations that appear in this paper you can find. And again, the derivation I produced here is completely general, applies to a multivariable case, and in spirit, of course, also to all other blocks for spinning blocks and so on and so forth. Now, I highlighted a little bit, I should, I guess, conclude. I highlighted a little bit structure. So the message I wanted to convey here is mostly, of course, these Hamiltonians that you get by studying harmonic analysis of conformal group. The relevant problem for the conformal partial waves leads to some nice Hamiltonians, but these Hamiltonians are really like just super nice. They have integrability with respect to coordinates or cross ratios, and integrability with respect to dependence on the spins and dimensions. And of course, that gives rise to many, many formulas, explicit formulas one can derive. In fact, in the case of ordinary hypergeometric functions, I mean Gauss hypergeometric functions, from the story you can derive all the recurrence relations or contiguous relations, all the properties, standard properties of hypergeometric functions, and they possess a straightforward, or not straightforward, I mean through this integrability, a generalization to this multivariable case. And in that sense, it is a solvable problem. Now, I've focused a little bit more on sort of general overview of structure than on concrete results. Maybe I want to show you at least one concrete result that you can obtain from here. That's taken from a paper Misha and I wrote last year. That's, for instance, a series expansion for a conformal partial wave for a scalar 4-point function, two-variable case, an explicit series expansion, in fact, in terms of these radial coordinates. Okay, so that's one of the formulas that you can obtain from this embedding. Okay, it may not look super nice, but it's a nice series expansion. I mean, it's a series expansion, okay, that correctly describes, I mean, so it's in some sense the analog of the usual series expansion of an ordinary hypergeometric, a Gauss hypergeometric function. And this actually works, the series expansion works for arbitrary values of lambda 1, lambda 2, so you don't have to restrict to integer spin in order to use that. So this is just to give you one example, because I was a little afraid that I kind of talk more about structure than about results. So just to show you that there's also results that you can get from all these words. And the mathematical literature and also our papers contain many more of such results. But of course, not everything that you would want to have has been derived. So coming to a conclusion, I wanted to come back to this problem, because I highlighted at the beginning that one of the issues was, even again in the classical book, was to construct the 6J symbol, or the crossing kernel, which is really an integral over T and S channel conformal block. Okay, and now you see that's why I kind of in particular walked you quickly through this dual story. So I showed you, so when you take this integral over S and T channel conformal block, you integrate over the cross ratios. So this object will be does not depend on cross ratios, it only depends on weights and spins. But I showed you, or told you, motivated or whatever, hope to convince you that these conformal partial waves, the dependence on spins and weights is also determined by an integrable quantum mechanics problem, namely by this Roisener-Schneider problem. So we can control the properties of this object, which is only an object depending on spins and deltas, through this Roisener-Schneider difference equation. And in fact, we are right now trying to do this in order to really obtain explicit control of this crossing kernel. So I now wanted to only argue that somehow for this, of course, to understand this object, it's much more important to understand not that there's a Calogero-Sutherland Hamiltonian acting on the conformal cross ratios, but that there's the Roisener-Schneider Hamiltonian acting on the spins and dimensions. Now this brings me to the conclusions. So I hope even deviating a little bit from Ivan's advice, I kind of had two messages in this talk. The first one was that conformal partial waves, even in the most sort of modern version of what you think of a conformal partial wave for all sorts of types of observables, even non-local observables, they're always wave functions of a Calogero-Sutherland Hamiltonian. So this is a very flexible framework. You can plug in whatever problem you have and essentially end up with some concrete quantum mechanics problem of this type. And on top of that, I hope I convinced you that this statement is not just stating, okay, giving a different name. I mean, saying conformal partial wave is just a wave function, but this statement is actually very powerful because these wave functions are wave functions of an integrable quantum mechanics problem, and so there's a lot of technology that applies that you can use to derive series expansion. I showed you a formula in one particular case, recurrence relation integral formulas, and so on and so forth. And of course, with that, I want to conclude. Of course, I shouldn't say that this has been completely developed. I think this new chapter of the book is really work in progress, but now there's a sort of a clear route to work it out, and sort of the mathematical foundations for this new chapter, in fact, were laid starting from the late 80s, again, through the work of many mathematicians, and through what I've explained to you, it really enters now into this theory of conformal partial waves, and really, I think, solves the problem of identifying conformal partial waves with some concrete hypergeometric functions about which a lot is known. But again, these are hypergeometric functions that people did not know about in the 19th century. It's a very modern branch of theory of hypergeometric functions. Okay, with that, I want to close.
The solutions of Laplace equation in terms of some invariant variables give Calogero.
Yeah, that's a very old observation.
Yeah, it's a very old results, and actually Olshanetsky, Perelomov classified all these kinds of things. But one thing I wanted to understand, in their case, of course, the more you, the bigger is the rank of the group, the more you have variables.
Yeah, so they have a different concept.
What is the role of U and V? Because for any dimension, you have only two of them.
Right.
Yeah?
So
what is the role of U and V in this picture?
In their original paper, they studied the different. So it's right. I should have probably mentioned this. So this relation between harmonic analysis problems on groups and Calogero-Sutherland, of course, is long known since the late 70s, I think, work of Olshanetsky and Perelomov. And in the original work, they looked at a different coset. It's G divided by, sorry, I should write it like this, G, where this G acts by the adjoint action, okay? And so this actually is a problem that, I mean, this quotient has as many variables as the rank of the group. Yes. And so they get a different Calogero-Sutherland model. It's attached to a different root system, the AR root system, where R is the rank of the group. Okay, but it's the same spirit of.
No, but my question is why? What is the role of UV variables in this picture? In this quotient.
So the UV variables now in conformal, I mean cross ratios.
Yeah, in cross ratio.
Right. So
for whatever is dimension, that means the rank of the group. You get two variables. It's some reduction, probably.
No. So I mean, so here, first of all, it's a different quotient, right? So it's a quotient by left and right. So it's G divided by k times k. Okay, so it's a different quotient, and this quotient is always two-dimensional. Okay, so you get only two variables, and so you can introduce these two variables like you do in that case. I mean, these are some. You parameterize basically Cantoros, right? That's the variables there. And similar here, you have, as I said, I call them generalized Euler angles on the conformal group, which make it into these variables. Okay. Then you can ask, how are these variables related to the usual cross ratios that people introduce, 4-point cross ratios? And in fact, I probably didn't show you the formula, but these Euler angles are essentially these radial coordinates that Slava and Matthias introduced. And the relation to the u's and v's and z's and z bar, whatever you like to use, is more or less the same relation. Okay?
Do you uncover these other variables when you take spinning blocks?
So no, spinning blocks, don't have more cross ratios. They have, again, then it grows in a different direction. But you can do, as I said, the other variables, some other variables you can, that's what I said. So when you, for instance, want to study Wilson lines in the four-dimensional gauge theory, right, you get three variables. So the k's change a little bit, and you get more variables, okay? And so then you can grow number of variables up to some maximum dimension. There might also be other conformal partial waves that are directly related to these AN Calogero-Southern models, okay? And so, but again, the problem I discussed here, this correlation function of defects or operators, leads to a different COSAT model than the original Olshanetsky-Perelomov paper.
Okay.
Okay, you don't seem like I answer. So maybe I can give the rest of the answer in conversation after.
Questions?
I was told the other day by Gemma Hock here that another new branch of hypergeometric function, Johann Chudzinski functions, are entering into interpretive conformal theory and string theory. Are there also relations?
Of course, there's a bunch of hypergeometric functions about which people have made progress in understanding. So precise relation of this class of hypergeometric function, which I think is probably closest to, maybe in some sense closest to the Gauss hypergeometric function that one can imagine, to these that appear in amplitudes computation is not quite clear to me. I think it's an interesting question. In fact, so I think it doesn't really have an answer. But of course, you can see many things. For instance, there's all these appearance of polylogs, let's say. And if you have Knittchen-Samolotchikov equations, polylogs are very intimately tied to Knittchen-Samolotchikov equations. Knittchen-Samolotchikov equation, as I showed you, appear in this context. So it's quite feasible that the hypergeometric functions that appear in amplitudes computation are also related to some of these hypergeometric functions here. But I think this is not really understood. In fact, we had thought about some of these issues a little bit, but without very conclusive results.
You mentioned at the beginning of your talk, you mentioned spherical,
spherical harmonics? No.
Yes, spherical functions.
Okay.
Oh. They appear in the.
Oh, you mean in the integral in the beginning?
Yes, exactly. Do they appear in the?
No, basically our task was to perform this integral, right? Somehow it's like when you,
There's almost spherical function.
Yeah. So this is they appear in the integrand, right? And like when Ivan just pointed out some. Like in the amplitudes world, you have certain things that you build your Feynman integrands from, and then you want to integrate. And so our task somehow, my talk was basically about performing this integration, right? And so, of course, the building blocks in the integrand are very different from the building blocks of the integral. And so this is about performing this integral and identifying the functions that right.
Right. So you mentioned that you can use these techniques to compute thermal blocks,
And I just wanted to ask, how does this work? Because it would seem that the compact time circle would break a lot of conformal symmetry. So how would you use this?
Okay, maybe. Okay, first of all, I have to probably specify what precisely I meant. Maybe we keep this also for private conversation.
All right.
This is not really worked out so well.
Could you imagine some deformation of this setup where you would get quantum Knight-Zamolodchikov equation and maybe some quantum version of spectral duality?
Of this duality. So I'm not sure that, but so you might have said, I mean, the free particle that I had in the beginning, I mean, that I showed you a few slides back. Sorry, that's a few slides back when I was at the end, but not from the beginning anyway. So you remember the free particle, right? So you had the same Schrödinger equation in U space as you had in P space. Now then I showed you the Calogero-Sutherland, and I argued that in this case it cannot be the same in U and P space, so it led to a shift equation. Right. So then you can wonder, I mean, can you improve on that? And I think the problem was somehow that our original Calogero-Sutherland, or let's say the difference equation that we had, I mean, Reusener-Schneider, was a shift equation, so an exponential of a derivative on one side and rational in lambda. So the idea, of course, would be to make it trigonometric or hyperbolic in lambda. So that's a Q deformation. And so you end up with the trigonometric or hyperbolic Reusener-Schneider equation. And then you would expect that it's self-dual. Okay, so the dual equation, and that's in fact the case. So then the dual equation, which is some kind of discrete version of Calogero-Sutherland that I showed you, is actually sort of discretization. But I mean, there's a discretization of this Calogero-Sutherland problem that looks the same as the Reusener-Schneider.
Is there an interpretation in terms of conformal blocks?
I'm not aware of a direct interpretation. It's, of course, there could be some kind of Q-deformed conformal field theory, but I think this is different. So in some sense, it's, for me right now, I mean, it's a technical device. The theory, of course, becomes somehow a lot nicer when you perform this deformation because you have self-duality between momenta and cross ratios somehow. And then in the end, you always have to take a degeneration to get the function that you're really interested in. So as a technical device, it's useful whether you can give interpretation to these objects independently. I'm not quite sure.
When you change basis from one channel to another one, you change not only the parameters, but you change the space. And it's kind of a discrete transformation from one to the other, so something like SL2Z. Can you feel this discrete transformation within all this?
Sorry, I'm not. So the discrete transformation is what? Not
changing, say, the two variables. In one channel, you change, say, U2 to 1 over U, 1 over V, or these three channels correspond to certain.
I mean, you mean now the action on the variables on the cross ratios?
Yes. Why is this action hidden somehow in this group?
Yeah, can I give a good answer to this? I mean, again, all this produces is a set of basis functions, right, in which you expand the T-channel block. I mean, the action of this transformation on the variables is sort of an external information to this. But I mean, you have the basis set of functions, and you just expand in functions of the dual variable. Okay, since this question keeps coming up and I still seem to not be able to fully understand what it is, maybe we discuss this also after the talk.
Yeah. Well, I'll take the liberty to ask the last question. So it's more like a comment. So right now there is kind of two types of theories of conformal blocks. There is a practical theory of conformal blocks, which is motivated by the desire to like do concrete computations with them. And then there is a mathematical theory of conformal blocks. If you look at the papers of Dole and Osborne, there are hundreds of equations there.
Yeah.
And actually, none of those equations are currently used to do any computations, because what people found are some very powerful recursion relations going to the work of Alyosha Zamolodchikov. And then the so-called weight shifting operators that in practice, as far as the practical computations are concerned, there are other techniques to compute conformal blocks which are being used every day. Now, on top of Dole and Osborne, you produce this beautiful theory which adds even more equations and some serious expansions which so far fit in one page. But can you tell us, like, can you tell practically minded people how perhaps there is something that we should be using more efficiently that we are currently using? Because we are not using any of these, and we are doing just fine.
I don't think for scalar, as long as you're interested in just scalar,
no, not just scalars,
local fields, 4-point functions, I think everything can be found in the Osborne paper. Probably not in the most beautiful way you can write it, but it's all there.
No, but you are wrong. You are wrong. Those formulas in the Osborne, they are not suitable for doing practical computations, because they are written in terms of, and not just for scalars. If you look at the analysis of the stress tensor 4-point function, this has been done without using any of these formulas that you are showing. So people found alternative techniques that you have not cited.
Sure, I didn't, was not very good.
So what is the relation between that theory and your theory, and is there something in the existent, currently used theory that should be changed?
I mean, so let me say, like, one of the applications that we are working out right now is, I mentioned that briefly. So for instance, super blocks, when you have long multiplets, right? That's something, so when external fields sitting in long multiplets of the superconformal representation algebra, that's something that actually only in very special cases people can write down. Of course, these super blocks might be, to know them and to do bootstrap with them might be very useful. It's a way of kind of studying mixed correlators. And so we demonstrated that in work with Magdalena Lemos in 2D, that, I mean, doing bootstrap, for instance, with long multiplets in supersymmetric theories is actually very constraining. But the problem is, I mean, except for a few special cases, nobody can write down the blocks for these super multiplets. So one of the direct applications that I didn't have time now to show, but there is a beautiful way of systematically constructing these blocks for long super multiplets using this theory. Okay, so that's just one example. I mean, everything I told you about, I mean, even you say from the bootstrap point of view, you may be not so interested in having correlation functions of defects or higher dimensional operators, but I mean, these formulas that I showed you, I mean, you could have gone through all the Dole and Osborne analysis, case by case, for any type of number of cross ratios, but I'm saying that this is completely universal, so everything that is appears in this paper for the two-variable case also appears for these defects. Whether that's relevant for the bootstrap or for other analysis of observer correlation function conformal field theory, that's of course a different question. But again, I would not reduce the understanding of conformal partial wave to the conformal bootstrap. In fact, whoever deals with conformal invariant quantum field theory needs conformal partial waves, right? So is that a partial answer? Or?
Conformally partial wave.
Yeah, so let's first of all thank Volker for his very nice talk. And so there were tons of questions, and our next talk was supposed to be at 11:30, but can we